Okay, so we talked about solubility in a previous chapter. Do you recall? Low solubility and soluble. Okay, so let's just turn to the next page. And do you recall the solubility table? Okay, so the solubility table is used when you're trying to predict whether or not a product will be soluble in water or whether it will have low solubility. So this you don't memorize, right? This will always be given. And you want to use it to determine whether the product that you form is soluble or has low solubility. So use it to determine the state of matter of the products. Okay, so there are only really two choices for the state of matter on products. That would be whether it's a solid, which means it's a precipitate, or it's soluble in water, which means it has AQ. So if it has an AQ after it, that means it's soluble. And then if it has an S after it, that means it has low solubility. And this would be known as your precipitate. And that's pretty much all you would use the solubility table for, okay? Today we're going to focus on writing something called net ionic equations. So basically we're mixing solutions and we're seeing if that solution produces a solid. And then we write the ions that are floating around in solution, and then I'll show you how to get the actual reaction taking place in solution, okay? So we're going to look at the next page. This page, actually. Okay, do you guys have all this written down? Can I make it a little bit bigger? Yeah? Okay, so let's come over here. And there are three different parts that we're going to focus on. And I outlined these parts on the worksheet that you got as well. Okay, so the first part is called the formula equation. Sometimes they're going to call this the molecular equation. They mean the same thing. The formula equation is just the balanced chemical reaction, and it needs to have the states of matter on it, okay? So here you're going to notice that we've got a solution of potassium iodide, a solution of lead-2 nitrate, a solution of potassium nitrate formed, and then you have a solid lead-2 iodide. That was my precipitate, okay? So let's just make a note here that we need the states of matter. Okay? Okay, once you have your formula equation, then what you do is you break everything down, and I'll do this in a different color. You're going to break down anything with an AQ. And I'm going to highlight these in green. So that means this, this, and this are the ones that I have to break down into ion form, okay? And I'm going to do this slowly because it can be kind of detailed, and I want to make sure you understand where I'm getting the charges from, so that's why you need to reference your periodic table with all the nomenclature notes on it while we're doing this, okay? Okay, so do you see how here I have a coefficient of 2? So if you have a number in front of a solution, make sure you distribute that coefficient to each one of the ions that come after it. So here I've got 2 Ks. What's the charge on K on the periodic table? Plus 1. Okay, so here is my 2K plus 1. Does that make sense how they got that? Okay, and then I've got 2 I's. What's the charge for I on the periodic table? Minus 1. So that's why they wrote 2I minus 1. Okay, and then for the next compound, there's no coefficient in front of this lead-2 nitrate. So I have a lead ion, and remember how we determined the charges on transition metals a long time ago? How we started on the right-hand side? So this NO3 right here, you have 2 of these NO3s, but the charge for NO3 on the periodic table is what? A -1. And then I only have one lead here, so that means it would be a +2 charge. That's because I have a -2 on the nitrate, so I have to have a +2 on the lead. So when we go to write this in ion form, I have a lead +2 ion here. And then since there are parentheses around the NO3, I have 2 NO3s, but that little 2 has to go in front, like it is right here. So anytime you have something in parentheses, the number on the outside goes in the front. So I have 2 NO3s, and the charge on NO3 is a -1. On the product side, I have a 2 in front of the KNO3. So you have to distribute this 2 to the K, and then it has to go to this NO3 because that's a polyatomic ion, okay? So on the product side, I've got 2 K plus 1s, and then I have 2 NO3 minus 1s. You don't touch solids, you leave them alone, right? Because we only break down things with AQs. What we just did is called the complete ionic equation. So what this is showing you is that if you could see what is in the water, you would see all of these ions floating around, and then you'd see this solid clumped up, okay? Okay, now the next part is where we write something called the net ionic equation. Now this is relatively easy to do because it's based upon what you did in this complete ionic equation, okay? So the net ionic equation shows you the ions that take part in the reaction. It gets rid of everything else. So how do we get rid of everything else? Well, whatever is identical on the reactant and product side, cancel. So do you see how we have a 2K plus 1 here, and then I have another one over here? So whatever you have on the reactant and the product side, if they're identical, you get to cancel them out. So this gets to go away. And do you see anything else that we can cancel? Yeah, this and this are identical. So these are also gone. And what you have left, that is your net ionic equation. Okay, so I just copy down the lead and the iodine. They changed the order of them. You don't have to. So here's my lead and here's my iodide. And then my product, my PbI2 solid, is over here. And the things that we canceled out up here, they're called spectator ions. They don't actually participate in the reaction. They watch the reaction taking place. So they say ions that are the same on both sides of the equation are called spectator ions. And spectator ions are like the spectators at a sports event. They watch the event, they do not take part in it. So that's why they are not included in the net ionic equation. Okay? That's it. That's basically the bulk of this entire lesson. Okay? So let's turn the page. And we need to do some practice, and then I need to talk about hard water briefly. So should we just do some practice? Yeah? Okay. So on the next page, they give us some examples. Okay, on your, let me just make sure, on your worksheet, I gave you reactants, right? And you have to predict the product. Okay, so let's practice that while we're at it. So let's take a look at number 2 is the one that goes through all 3 steps. So I think this is what's relevant. We don't need to do all 3 of them, but I want to at least do one of them. Is there one that you would prefer? Do you want to do B or C? B? Okay. All right, let's take a look here. Okay, here it says we're mixing solutions of magnesium sulfide and zinc chloride. Okay, so when we do this, it's been a long time. Remember how we wrote these out in words first? Okay, I know you probably don't want to do it, but it works the best. So magnesium sulfide plus zinc chloride. Everything that we're doing is a double replacement reaction. This includes the stuff that's on your worksheet, okay? So I'm going to highlight the magnesium. And the zinc, because these are the ones that are going to switch places. When they switch, what are the names of my products? Zinc sulfide and magnesium chloride. Okay. Okay. Now let's look at the periodic table. Let's get the symbols and let's get their charges and let's figure out how to write their chemical formulas. Okay. What's the charge on magnesium? +2. +2. So this is Mg +2. Sulfide is S. What's its charge? -2. What would my chemical formula become? MgS. Okay, so I'm going to leave a little space in front of MgS for us to balance it. And it says it's a solution, so I'm going to put an AQ after it. I don't need to look at the solubility table because they told me it was a solution. Okay, that automatically means it's dissolved in water. Zinc has what charge? +2. +2. What is chloride's charge? -1. What would the chemical formula be there? ZnCl2. Yeah, ZnCl2. They also said it's a solution, so I put AQ after it. Are we good so far? Okay, zinc sulfide. So zinc is Zn +2. Sulfide is S -2. This would become ZnS. We need to look at the solubility table to predict the state of matter on it. So sulfides with zinc would be what? Low solubility. So put a little S after it then, because it's low solubility. Then you have magnesium chloride. So this is Mg +2, Cl -1. This becomes MgCl2. Okay, this is actually balanced. So these are just ones. Okay, and what we just did is the molecular or formula equation. Okay, I usually label it over here. I don't have that much room. But there's the first equation, okay? I'm going to get a different color highlighter. Yeah.
Why didn't we check the solubility for MG?
Oh, sorry, I forgot. I know it's soluble. This is soluble in water. Okay. Now highlight anything that has an AQ after it. So this one, and this one, and this one. Okay. Now we can go ahead and we can write the complete ionic equation. This is where we break everything down into ion form if it has an AQ after it. Okay. Since we wrote a lot of the ion charges up above, I'm going to just use those. So magnesium is a +2. I've got one of them. So this is Mg +2. And then I have a sulfur, so this is S -2. Here I have a zinc, so it's Zn +2. But I have a subscript on the chlorine, okay? So you have to be careful here. There's no such thing as a Cl2 ion. So this little subscript 2 goes in front of the chloride ion, okay? And then I have my product, zinc sulfide. I leave it alone. I have a magnesium ion, and then again, I have this subscript 2 on the chlorine. There's no such thing as a diatomic ion, so this is 2Cl -1, okay? Now I'm done, and now I need to figure out which ions will cancel out because they're identical. Can you give me an idea? Wait, before you speak, let me